Hello and welcome to the Don't Sweat Hot Weather Concreting Know Your Options. My name is Eric. I will be your operator for today's call. At this time, all participants are in a listen-only mode. Later, we will conduct a question-and-answer session. Please note this conference is being recorded. I would now like to turn the call over to Scott Tarr. Scott, you may begin.
Thank you, and thank everyone for joining the webinar. As Eric said, I'm going to be talking about hot weather concreting today and what that is, how it's defined, and how it affects concrete and what precautions you can do. My name is Scott Tarr. I'm with North Star Concrete Consulting. We're based out of New Hampshire, but I work nationally and internationally, and today I'm actually in Itasca, Illinois. First of all, I'd like to say that, during hot weather concreting, there is a human element. And while I don't include that in my seminar, I do like to just talk briefly about it up front. In hot weather conditions, workers need to pay attention to their own limitations, overexertions, and make sure they stay hydrated. Not necessarily like this gentleman, but you do want to keep that in mind at any rate. Today, I really want to focus on the materials. We're trying to talk about concrete and how hot weather affects concrete itself. Some materials are meant to be placed in hot weather conditions, and other materials are not meant to be placed in hot weather conditions. So we need to take precautions, especially when we're placing thin concrete elements. Today the agenda again is what is hot weather concreting, the definition, effect of hot weather on fresh concrete properties, effect of hot weather on hardened concrete properties, and how to determine if hot weather may impact your project and precautions to take for hot weather concrete. ACI, the American Concrete Institute, has a Committee 305 on hot weather concreting, and they actually have defined what hot weather concreting is. And contrary to what you might think, it's not just a temperature-related phenomenon. It's really a number of different factors, which you see here: high ambient temperatures, high concrete temperature, low relative humidity, wind speed, and solar radiation. And these factors can come together in any combination to affect the concrete, fresh properties and hardened properties, by basically increasing the rate of moisture loss and the rate of cement hydration. And again, these factors can impair the quality of fresh and hardened concrete. Fresh concrete properties, because it will increase the concrete temperature, it affects the water demand. As the concrete temperature goes up, the slump and workability of concrete goes down. We can certainly counteract these influences by using admixtures, but sometimes this is hard to predict, and admixtures are kind of hard to dial in, and temperature conditions and weather conditions can change quickly. So if you use just water on the job site to influence the slump and increase the workability, that of course can influence the hardened concrete properties. You can see here, as the increased concrete temperature, the water content of the concrete mix to maintain the same slump goes up. Okay, you have an accelerated slump loss, so you need to be aware of that. Slump loss and the workability associated with that can decrease very rapidly on the job site. Increased rate of setting. This slide shows two different cement types, cement A and cement B, and it shows the initial set in blue, and the final set in lighter color, and the final set in darker color. And you can see that as the temperature increases from 50 to 73 to 90, the setting time of the concrete decreases. And the setting time really is very important, especially my background is really in concrete slabs. So when you're placing a relatively thin, relatively large concrete slab, the setting time is very important, and the rate of setting and your finishing operations will continue in the order that the concrete is placed. And you want a consistency in that set time so that you can get the appropriate finish and not run into finishing difficulties. Increased rate of plastic shrinkage cracking, and we'll focus on this a little bit later, but ACI 305 has a chart that allows you to determine the evaporation rate of the concrete. And the chart looks very difficult, but I hope to show that the chart really isn't very difficult to understand. But as the concrete temperature increases, the evaporation rate from the concrete also increases. And you need to be aware of what the important precautionary evaporation rates are, how to predict those or how to calculate those on your job site, and then what to do to counteract that. This is a typical slide of what plastic shrinkage cracking is. For those of you that don't know, plastic shrinkage cracking is a cracking that occurs during the finishing operations, during floating and during troweling. It actually looks like little tears. Generally, they are perpendicular to the direction of the wind, and they're generally a few feet in length and a couple of feet apart, and you'll see them in a series. And again, they kind of look like tears in the concrete. The finisher generally will see those, and he'll try to mend those back in with the next finishing operation, but it's something definitely to be aware of. Hot weather concrete will also affect the controlling the air content. If you have an air-entrained concrete mixture, as the temperature goes up, sometimes it's very difficult to control the air content, as shown by this slide. You can see concrete temperature on the bottom axis or on the top axis, and the air content on the left-hand side. And the last fresh concrete property is the increased potential for thermal cracking. This is usually in large mass concrete members or footings and things like that, large piers, and bridge abutments. But you can get a thermal cracking that can affect the performance of that concrete element. Here is a schematic of what happens. Internally, as the cement hydrates, it creates temperature rise. It's an exothermic reaction, the hydration of cement. So internally, the concrete stays very warm, and on the outside, you can get surface cooling. And if that surface cooling occurs, you get temperature contraction of the concrete, and you can get cracking. For slabs in particular, the time that this really happens is the first night after placing the slab. The inside of that slab is hydrating, so the lower portion of the slab is staying warm, and especially when it's in cooler conditions, the top surface of the slab is cooler. So as the top surface cools, it wants to contract relative to the warmer bottom surface, and that can cause early age curling. It's shown in this slide. Now, early age curling can be problematic because the stresses associated with that curling at a very early age, the first night after placement, can cause cracking. This is one of the reasons why we want to get our saw cut joints put in within the first 8 to 12 hours. Hardened concrete properties are also affected by hot weather conditions, and especially if you counteract those hot weather conditions with the addition of water. So as you add water to concrete, the strength development goes down. Hot weather will create an increased strength early on, as shown here at 1 day. You can see the warmer the temperature of the concrete, the higher the compressive strength. But at 28 days, the exact opposite occurs. You can see the concrete that's maintained at 120 degrees is actually the lowest 28-day strength, and actually only comes up to about 75% of the targeted 28-day strength. Other things is if you add water to a concrete mixture, you're increasing the drying shrinkage. And the drying shrinkage may not be a big problem, but if it is restrained, the restraint to drying shrinkage can cause cracking. So you can get increased cracking. Higher water-cement ratio can give you an increased permeability, and you can have difficulty finishing slab surfaces and get a non-uniform slab finish, a slab appearance. Surface defects such as dusting and reduced resistance to abrasion and salt scaling may occur if water is sprinkled on the concrete surface during finishing. So you want to make sure that you're not adding any water to the surface during finishing. Again, here's a picture of plastic shrinkage cracking, and it's a very high risk in hot weather conditions. Why is it a high risk? Once again, it's that evaporation rate from the concrete. So what are we talking about when we talk about evaporation rate? ACI 305 includes I guess it's a nomograph or a chart, and the chart has basically 4 factors, or 4 properties: air temperature, concrete temperature, relative humidity, and wind speed. And the chart looks like this. And it does look kind of daunting if you're not familiar with it. You look at this thing and you say, gosh, how does this work? Well, you use these 4 properties or these 4 characteristics to go in, and you can calculate fairly easily the rate of evaporation from the concrete. Let's take the example that's shown on there with the dotted line. The example that ACI 305 gives is air temperature of 64 degrees, relative humidity of 40%, concrete temperature of 60 degrees Fahrenheit, and a wind velocity of 20 miles per hour. So certainly not what somebody might think as hot weather conditions with an air temperature of 64 degrees. Let's go in. We start with air temperature, which is shown here on the chart, 64 degrees, and we head upward towards the red lines, which is the relative humidity. And the relative humidity in this particular example is 40%, so we start with 64 degrees and go up to 40% relative humidity. This line is a turning point. So you turn at this point and you head to the right towards concrete temperature. Concrete temperature in our example is 60 degrees Fahrenheit. So you go over to 60 degrees Fahrenheit on this blue line, and that's another turning point, and you head downward towards wind velocity. In our example, the wind velocity is 20 miles per hour. So you head down to the 20 mile per hour line, and you go to the left where you get rate of evaporation. So in this particular example, the rate of evaporation is 0.12 pounds per square foot per hour. The critical, or the rate of evaporation where precautionary measures should be taken is normally taken to be 0.2 pounds per square foot per hour. So that's kind of the number to watch for, especially when you're placing a large thin element such as a concrete slab, 0.2 pounds per square foot per hour. Well, let's take another example. Let's say an air temperature is 80 degrees Fahrenheit, so certainly a nice day, but not a particularly hot day, especially for those of you in the south. Relative humidity, instead of 40%, let's make it 50%. So not humid really, but not dry, right in the middle. Kind of a nice day. Concrete temperature, instead of 60 degrees, let's go for 85 degrees. As many of you probably know, the maximum concrete temperature recommended by ACI 305 is 95 degrees. So an 85 degree temperature of concrete is not particularly high. Wind velocity, 20 miles per hour is a little bit high, so let's reduce that down to 15 miles per hour. So these conditions here with 80 degree air temperature, 50% relative humidity, 85 degree concrete, 15 mile per hour wind, really doesn't seem like very dangerous conditions. However, if we go into the chart and we start with our 80 degrees air and go up to 50% relative humidity, over to 85% concrete temperature, down to a wind speed of 15 miles per hour, and over to an evaporation rate, even in these conditions, we now are at 0.27 pounds per square foot per hour, which exceeds the 0.2 pounds per square foot per hour. So in this case, precautionary measures should be taken, especially again with large concrete slabs that are susceptible now to plastic shrinkage cracking. A very high rate of evaporation from the slab can give you these plastic shrinkage cracks during finishing. How do we measure these weather conditions? This is oftentimes misunderstood. I do a lot of pre-construction meetings, and when the potential for hot weather concreting is there, I always like to discuss that during the pre-construction meeting, and we talk about how we're going to use this chart or how we're going to determine where precautionary measures are going to take place and what precautionary measures we're going to do. And most people like to just go to the nearest weather station and get the data from the nearest weather station. But I'll tell you, the nearest weather station really doesn't have that much influence necessarily on your project site. If you go to the nearest airport and the weather station is actually on the tower, you're measuring wind speed at a height of 50 or 60 feet. And that can be much different than the wind speed actually measured above your project. In fact, ACI 305 recommends that these properties be measured at a height of about 20 inches from your concrete element. So you really want to have a handheld or a tripod-mounted weather station right at your project to be able to get actual project conditions to know whether you're in the need to take these precautionary measures. And these devices are really relatively inexpensive. They're handheld units, and they'll give you all of the properties that you need. You've got wind speed, air temperature, relative humidity, and then your concrete surface temperature. You can either use a thermocouple in the slab, or you can use an infrared thermometer just to measure that slab surface temperature. So plastic shrinkage cracking, again, occurs during that rapid evaporation from the concrete. Precautions must be taken typically at 0.2 pounds per square foot per hour. However, when you use pozzolans, fly ashes, slag, that decrease the heat developed during the setting time of concrete, decrease that heat generation, decrease the strength gain or slow down the strength gain. A lot of people like to recommend that be decreased to 0.1 pounds per square foot per hour. And with silica fume, the recommendation is often 0.05 pounds per square foot per hour. So you can see how these materials can influence the potential for plastic shrinkage cracking and the time that precautionary measures are taken. So what are we talking about when we're talking about precautionary measures? When we're using hot weather concreting, what do we do? How do we prevent plastic shrinkage cracking or other factors that influence the concrete? Well, anything we can do to influence any of those four factors that are included in that nomograph would certainly change the evaporation rate. So let's go through those four factors. Again, they're ambient temperature, ambient relative humidity, concrete temperature, and wind speed. So we'll start off with ambient temperature. A lot of times people will say, erect a sunblock, create shade. And if you're looking and you're working on a large concrete construction, sometimes this just isn't feasible. You're probably not going to erect a large sunblock or tent over your project. If the project is relatively small, this may be easier done. If it's large, it's probably not very possible. However, if you are thinking about this, if you're going into the summer and you think that hot weather conditions may exist during the project when it's being built, if it's a slab, maybe some decisions are made to use precast concrete and erect the shell of the building before you do the slab to protect the slab from the sun. So that's one potential option. The sun and the temperature will affect the material as it's being delivered. So you can shade the equipment, you can paint it white, or cover it with wet burlap, just to kind of keep concrete temperatures under control. Forms, reinforcement, and subgrade should be dampened with cool water, and I'll talk about that in just a few minutes as well. Perform operations as quickly as possible. What happens during hot weather concreting is you shorten the window of finishability. There's a certain window. You don't want to finish the concrete element too early, and you certainly don't want to finish it too late. So there is a window of appropriate timing for finishing operations, and hot weather concrete operations will shorten that window of finishability. So you want to perform operations as quickly as possible so you don't miss the end point of that. Have an adequate crew size to be able to do these things. A lot of times we talk about in a pre-construction meeting reducing the haul time to the job site. The ASTM C94 spec on ordering concrete and on concrete mixing and delivery suggests that concrete should have a 90-minute time between mixing and placement at the job site. And a lot of times in hot weather conditions, you can reduce that time down to, say, 75 minutes, or maybe if the plant is close by, make that a 60-minute recommendation. You don't want to have stacked trucks. You want to have a lineup of trucks in hot weather conditions because, again, your setting time is decreasing, your slump loss is increasing, so you just want to be able to time your trucks appropriately. You want to avoid cold joints, so you don't want to have delays in concrete delivery, so you want to just have the trucks properly timed so that they're coming at the right rate so that you can get the concrete placed and in place on time. The most popular way to counteract hot weather concreting is to adjust the timing of placement. And a lot of times, most of the slabs that I'm involved with that are placed where hot weather can be an influence are placed at night. They may have a start time of, say, midnight or 1 a.m. to take advantage of the lower ambient temperatures at night. All right, let's talk about the second factor in that evaporation rate chart, and that is ambient relative humidity. Unlike temperature, you don't want to reduce the ambient relative humidity, you actually want to increase the ambient relative humidity. You want it to be more humid air because the evaporation rate will be decreased if the humidity is increased. So you want to make it more humid. And one of the easiest ways to do that is to fog above the slab and create a higher humidity air above the slab. And this sometimes seems like this is going to be a problem, but actually I've done this on projects, and it actually works quite well. Fogging the air above the slab and increasing that relative humidity will actually result in a decreased rate of evaporation. That's really the only thing that you can do to influence the ambient relative humidity. However, if that's not possible or not feasible, there are other options to decrease the rate of evaporation. You're not necessarily going to influence the ambient relative humidity, but you can use evaporation retarders. When I have seen these products used, I have seen them used improperly quite often. Evaporation retardants generally form what's called a monomolecular film. Sounds like a real difficult word, but basically that's a very thin film on the surface of a wet object. They were actually developed for the city of Phoenix, Arizona, to preserve their water supply. They have water facilities that are open to the air, and the water was evaporating in dry areas like Phoenix and Las Vegas. And monomolecular films were developed so that you spray them onto the surface of the water, and they spread out, and they do just that. They form a one-molecule thick film of water on the surface of the water to reduce the evaporation rate. So they can also be used on the surface of concrete. The trick is that you want to mist them on. You're going to apply these like a garden hose, which I have seen in the past. You actually want to mist them onto the concrete surface. They do form a very, very thin film. They do reduce the evaporation rate, but as soon as another finishing operation is done, they're gone. That one molecule is destroyed, and if there's a need to continue to control the evaporation rate, they need to be reapplied after that finishing operation. So they need to be reapplied as necessary. It's typically not recommended to be applied after or during the hard troweling, final troweling operations. All right, I don't see this very often, but another way to retain moisture in between finishing operations on some concrete elements is to cover it with a polyethylene, sheet of polyethylene. That will preserve the moisture in the concrete until the next finishing operation can be performed. Curing. Curing should be done as soon as possible or as soon as practical, and this is always a tough one. It's easy for someone to say as soon as possible or as soon as practical, but how soon really is that? For slabs, usually that is not until after joints are saw cut. And we can talk about doing it prior to that, but if you put a curing cover down prior to saw cutting joints, somebody has to pick the curing cover up to cut the joints and then put it back down. It's just not practical. If you use a curing compound, it tends to gum up the blades. So really that is something that's done after saw cutting. There's several ways of doing curing. Moist curing, there are some moisture-retaining covers that are recommended. For slabs, we don't recommend flooding or ponding with the slab very often because what happens is that the excess water penetrates into the joints or around the edges and gets into the subgrade and can cause issues. Ponding or constant sprinkling or the use of perforated hoses, garden hoses, really aren't recommended anymore most of the time. Instead, there are some very effective high absorbency rolled-on covering materials that absorb the water and preserve it. Generally, you don't need to add any additional water when you're using one of these types of materials, and you can get a nice moist cure. What is the typical length of the curing period? Really is project dependent, but typically for a slab, we like to see at least 5 days. 7 days if it's possible, but 5 days of curing is typically acceptable. The old research at the Portland Cement Association showed that if you can keep concrete moist and curing for a period of 7 days, it will reach its 28-day strength. So that's where the 7 days comes from, and that's been shortened to 5 days, and in some cases I've heard recommendations of even 3 days. But I would question that and certainly have that be on a case-by-case basis. The water that's applied during the rolling on of these high-absorbent materials or any type of water-applied curing, you need to be careful about the temperature. Remember that concrete slab, especially in hot weather conditions, is hot. The temperatures of these things can be well over 100 degrees, and if you're using city water or well water, a lot of times that's pretty cool water. So when you add cool water to a hot concrete element, slab, you can get rapid temperature contraction, which actually leads to craze cracking. Craze cracking, as we know, can result from high evaporation rate, early age drying of the concrete surface, but a lot of times if you add very cold water to the concrete slab surface early on, it can result in that early age temperature contraction as well. So the recommendation is the water should not be more than 20 degrees Fahrenheit cooler than the concrete surface. You can still roll on polyethylene onto the concrete element. The precaution for this one is that if it's concrete that's going to be exposed to view, a lot of times you'll get discoloration. You'll get a pronounced modeling effect. It's called the greenhouse effect, where the polyethylene is in contact with the concrete surface can be a different color than where the concrete is not in contact. So at the wrinkles of the plastic, you can get a different color. And sometimes this can be very pronounced. Waterproof papers are available also to, again, retain the moisture. You're trying to keep that rate of evaporation down. And curing compounds, of course, very popular. In hot weather concreting especially, we recommend that the curing compound be an ASTM C309 compatible product. And these are membrane-forming products. And more than that, really, they need to have a water retention. They need to pass ASTM C156 on the water retention capability. For example, a evaporation retardant forms a membrane. That membrane is 1 molecule thick, but you wouldn't necessarily use that, wouldn't be recommended to use it, as a curing compound. Even though it's membrane forming, it doesn't conform to ASTM C309. So they need to be, especially in hot weather conditions, they need to be membrane forming and water retaining curing compounds. Let's talk about the third factor on the ACI 305 evaporation rate chart, which is concrete temperature. Many ways to change the concrete temperature. ACI 301 specification for structural concrete says that unless specified or permitted, concrete temperature as placed shall not exceed 95 degrees Fahrenheit. And that was adopted at the latest ACI 301-10 from the latest ACI 305 recommendation on hot weather concreting. It also goes on to say in the same paragraph, when temperature of reinforcement, embedments, or forms is greater than 120 degrees Fahrenheit, use a fine mist of water to moisten the hot surfaces immediately before placing concrete. The one critical thing here is remove standing water before placing concrete. Don't want to leave that standing water necessarily in the form. All right, how do we reduce concrete temperature? First of all, if you wanted to, you could calculate the concrete temperature. It's a very daunting looking equation, but really all this really says is if you know the temperature and the mass of all of your concrete components, you can add them all together to form the ultimate concrete temperature. So temperature of the cement, say, coarse aggregate, fine aggregate, and mixing water, all combine with the mass of those constituents to result in your ultimate concrete temperature. I don't see this type of equation and this type of analysis done very often in the field, just because it's difficult to have the temperature of all of these elements. Most people say if we're going to reduce the concrete temperature, let's put colder water in. Let's just try reducing the temperature of our water, our mixing water. If we cool that down, we should be able to cool down the concrete. Unfortunately, though, the water component of the concrete is not very much. There's not a lot of water usually in a yard of concrete. You're typically talking about 30 to 32 gallons, say, of water. In comparison to the aggregate content, the water is very, very low. So here's an example of trying to reduce the water temperature to cool down the concrete. Let's say we have an aggregate temperature of 100 degrees and a water temperature of 55 degrees, and we have an ultimate concrete temperature of 93 degrees Fahrenheit. If we reduce the water temperature by 5 degrees, we're only reducing the concrete temperature by 1 degree. If we reduce it by another 5 degrees, we may get another degree or two out of it, but really not typically an effective way just reducing the temperature of the water of reducing the ultimate temperature of the concrete. Rule of thumb is you can get a 3.5 degree change of water will give you 1 degree change in concrete temperature. Difficult to achieve more than about 10 degrees Fahrenheit change in concrete with water alone. Well, we can really decrease the temperature of water and create ice. And if you try adding ice to the concrete, you can actually achieve decreases in temperature of up to maybe 20 degrees Fahrenheit. So it can be effective in many cases. A couple of things to be aware of. You need to make sure that the volume of ice does not exceed about 75% of the batch water. Also, the mixing time must be long enough to completely melt the ice. Let's talk about cooling the aggregates. The largest volume in a concrete mixture is the volume of the coarse and fine aggregates, coarse aggregates especially. If you can reduce the temperature of those aggregates, you can have actually a pretty decent impact on the resulting concrete temperature. Let's take that same example of 100 degree aggregate temperature and 55 degree mixing water temperature resulting in 93 degree Fahrenheit concrete. If we reduce the aggregate temperature by 5 degrees, we actually get nearly a 5 degree temperature drop in the concrete. In this example, it's 4 degrees, but pretty close. Cooling coarse aggregate by just 2 degrees, as a rule of thumb, can result in a reduction of concrete temperature of about 1 degree Fahrenheit. So, as a rule of thumb, 2 degrees, every 2 degrees in your aggregates will give you 1 degree in your concrete. How do we cool the aggregates? We can talk again about erecting sun blocks, and that's maybe practical in some areas. There's even some areas that have the capability of refrigerating aggregates and reducing the temperature of the aggregates. Not really very common and not necessarily practical. The most practical thing we see, of course, is sprinkling the aggregates to keep them moist, using cool water, well water, to sprinkle the aggregates, and that can typically result in a pretty decent reduction in the temperature of the coarse aggregates. Let's talk about the concrete mixture. What can we do to the concrete mixture that can affect the concrete temperature? Well, we can use different components. We talked a little bit about fly ash, slag, things that result in a lower heat of hydration. These constituents can be added to concrete. You need to be aware, though, that when you're adding this, you may have to decrease the evaporation rate before taking additional precautionary measures. They will impact the early age strength gain. Low heat of hydration cement, like type 4 cement, can also be used. But we're talking about the heat of hydration of the cement. The cement itself, of course, has a temperature to it. A temperature to the cement powder will actually can have an impact, and that usually is relative to the time that it was ground and the storage conditions. They're stored in cement silos that can reach incredibly high temperatures. And in general, a 9 degree temperature change can result in a 1 degree concrete change. So if you can reduce the temperature, the actual temperature of the cement powder, you can reduce the concrete that way as well. You can use less cement. So you get about a 10 degree to 15 degrees per 100 pounds of cement. Now, a lot of times it's not possible to decrease the amount of cement. You're looking for a certain strength. You're using that cement to give you a certain water-cement ratio, a certain durability. But it's surprising how many concrete mixtures you evaluate and you wonder why the cement content is so high. So there are cases when you can reduce the cement content. That will certainly reduce the temperature of the concrete, and it will also reduce the potential for shrinkage of the concrete and dry and shrinkage-related cracking. If you reduce the cement content, you're probably going to you want to maintain certainly the same water-cement ratio, so you're reducing the water content. And by doing that, you may need to use admixtures to increase the workability in the slump. You may need to use a water-reducing admixture or a super plasticizer. You can also use a set retarder to retard the setting time, to prolong that workability and give the finishers a little bit more time to work with on the site. The other admixture I'd like to talk a little bit about are micro polypropylene fibers. While they're not recommended necessarily for controlling the drying shrinkage cracking in concrete, when we're talking about hot weather conditions and the potential for plastic shrinkage cracking, this really is where polypropylene, plastic microfibers, do give us some benefits. I have not done this myself, but you can use liquid nitrogen to cool the concrete in extreme conditions. Now, this isn't necessarily the least expensive method, and that's why I'm putting it here on the bottom, but liquid nitrogen is at a temperature of about negative 320 degrees Fahrenheit. And when you add liquid nitrogen to concrete, it immediately boils. And that boiling vapor gas flows through the concrete and cools it by heat absorption. So you can actually use liquid nitrogen. The gas escapes, and there's no permanent effect or residue left in the concrete. It cools the concrete down, and there's no replacement of mixed water necessary or anything like that. It's just a method of cooling the concrete. Talk a little bit about wind velocity. Of course, like shades, erecting shade blocks, sun blocks, the number one recommendation is usually wind blocks. And usually when you're at a pre-construction meeting, this is where the crowd just kind of chuckles or gasps like we're going to erect a special fence or a wall to keep the wind off of our project. But remember, ACI 305 recommends that wind speed be measured at a height of just 20 inches above your concrete element. So we're not talking about erecting necessarily a 30-foot wall. We're talking about something like 3 feet, 4 feet. Some type of a wind block, something like this, actually can be quite effective in controlling the wind velocity just above your concrete, and therefore certainly have a positive impact on the evaporation rate from the concrete. Wanted to talk a little bit about control tests, especially during hot weather concreting, and this comes up in virtually every pre-construction meeting that I'm involved with, whether it's hot weather concreting or not. Really important to take care of your concrete cylinders. Concrete cylinders are cast during the project, taken to a lab, and the compressive strength is usually measured. If the compressive strength of those samples comes up low, red flags go up, something needs to get done, an investigation needs to be performed to find out why the concrete strength is not coming up to the specified strength. Really important to take care of these cylinders at a very early age. Can't tell you how many times I've gone to a job site and the cylinders are sitting there exposed to the sun, just baking in the sun and drying out. And they can be capped, but very often they're just sitting off to the side with absolutely no protection. And they need to be stored at a temperature between 60 and 80 degrees for the first 48 hours. So you really need to make sure that that is done. If it's higher strength concrete, that window of temperature is actually reduced to between 68 and 78 degrees Fahrenheit. You really need to use some kind of a storage container that maintains the temperature. If you're doing cold weather concreting, you don't want the cylinders to freeze. You want to put them in an insulated box with some type of a heating element. If you're doing hot weather concreting, you want to put them also in an insulated box with something that cools them, either ice or very often you'll see them in a horse trough. It's called. You put the cylinders in the water just to kind of try to maintain them at that recommended temperature range of 60 to 80 degrees. So one of the biggest recommendations here as we're going through with hot weather concreting, all of these things need to be discussed. during a pre-construction meeting. And pre-construction meetings are always recommended on every project, but it's especially important to talk about these things so that we know what to expect. What is the ready-mix supplier capable of doing if we get to these conditions? What is the cost of that going to be? Who's going to pick up the cost of that? Is that in the budget? These things really need to be considered and discussed very thoroughly in the pre-construction meeting. And sometimes those meetings aren't necessarily all that fun to sit through, especially if you're the one that's being asked to do extra work or provide an extra budget. But they're very, very important. You don't want to get to an issue on a project site and have to then start a discussion. Very highly recommended to have that discussion prior to having the issue. So that is the end of my presentation. I think I'm right at about 41 minutes, leaving about 20 minutes for questions, and I'm happy to open that up, Eric. I don't know how that's done, but why don't we open up the microphones?
Certainly. And we will now begin the question and answer session. If you have an audio question, please press 0, then 1 on your touch-tone phone. If you're using a speakerphone, you may need to pick up the handset first before pressing the numbers. Once again, that's 0, then 1 to ask your audio question. You can submit web questions via the chat box located in the bottom left-hand corner of your screen by typing in the space provided and pressing enter. Okay, we do have an audio question from Tom Ralston. Please go ahead.
Hi, thanks for the presentation. It's very informative, and I appreciate that. I wanted to ask a question about when concrete actually starts to crack, and you said 8 to 12 hours. I've heard it as little as within the first 6 hours, or at the 6th hour. So that was one thing, and the other thing was I do lots of decorative concrete, so there's so many things that we cannot do, the ultimate taboo being plastic, as you pointed out. But even curing blankets sometimes aren't acceptable. And what we've found is that if we continue to mist it, not flood it, but mist it, that we've had really good success with that. And so those are two of my first questions I had or comments.
Excellent questions and comments. Yeah, that's very, very good. Your comment about the cracking, and I guess I need to be careful to differentiate between what we were talking about earlier in the program as far as plastic shrinkage cracking. And that cracking occurs certainly much, much earlier than 8 to 12. The cracking that occurs at that time period, and 6 hours certainly isn't unheard of. That would be, more of the temperature contraction cracking, the drying shrinkage cracking that occurs early on, that you want to have your joints sawn by. And when I say 8 to 12 hours, I generally will recommend that as a maximum.
Okay.
You can, in certain weather conditions, I think you can still get away with about maybe a maximum of 18 hours, but, it really is very weather dependent. I've seen, it used to be that people would come the next day with their, conventional diamond saws and start saw cutting. And it's interesting, when you have a drying shrinkage crack issue, you may get away with the first half of your saw cutting operations, and you'll find that your cracking started, at some point during your saw cutting operations. So you were right on the cusp of the end of that time limit. Certainly in certain weather conditions, and hot weather conditions are, those conditions, 6 hours is absolutely not unheard of. It's really highly recommended to use early entry green cut saws. And they can be on there within just a couple of hours after the final finish. So, good comment. Thank you for pointing that out.
And thank you. And one last thing, if I may, is the admixtures that can be used, the water reducers, the super plasticizers, high-range water reducers, etc. You didn't really get into that, but isn't that a great and effective way to increase the flowability and reduce the water-cement ratio? And I think that is at least for our operations, has been fairly key as well. Can you touch on that?
Absolutely. It's rare these days that you get to a project and you don't have any admixtures. I don't remember the last project that where that happened. I think what I intended to portray there is certainly they're a great way of increasing the workability, increasing the properties that you're looking to do. I mean, there's an admixture for everything: set retarders, water reducers, super plasticizers. To be honest, for slabs, which is actually really what my specialty is. For slabs, I prefer a mid-range water reducer over a super plasticizer, and the reason for that is because what I've seen with high-range water reducers is very difficult to control the timing of setting. You don't get necessarily a real consistent setting time, and that for slabs is really important because you're going to finish that slab in the same order that it's placed. So you really want that slab to set at the same order as it's placed. It's very difficult to pick up your finishing equipment and jump over a soft spot or go around it and come back to it. So I have nothing really against high-range water reducers, but I've seen that the consistency of set time is more difficult to control when they're used. Mid-range water reducers I've seen fairly decent performance with, and you're absolutely right. It's a great way to control it, especially if you know that what the conditions are going to be, and that they're not going to change. It's really difficult if you're working in hot weather conditions that are changing, becoming hot weather. If you're doing something during the day and you start in the morning, and by noon, your weather conditions are completely different. It's a challenge for the supplier to dose that properly. I mean, they're constantly making small adjustments to the admixtures, and it's a challenge to keep that workability by adjusting admixtures. So a lot of times it gets to the site, and the only adjustment that can be made at that point is the dreaded, addition of water, which we're trying to avoid.
I just wanted to comment. We just got back from a project in Aruba, and they don't allow water to be added on the site. They have very arid, dry conditions, very windy, and very hot. So they have all the elements pretty much working against them. So we did everything we could, wind blocks and shade, etc. But when the concrete comes and you want it to be a little bit more workable, they add a water reducer, some kind of a plasticizer, and I'm going to ask exactly what that was. But have you ever witnessed that?
I have. The thing that you need to be aware of, I typically don't like to have chemicals added at a job site.
Okay.
And I say typical. I'm not necessarily against anything, but just in general, when you add a chemical, you've got to make sure that you adequately mix that concrete and make sure that the chemical is taking the effect that you're looking for. I typically encourage an addition of water. What you need to make sure of is that you have a holdback water. So the ready-mix plant needs to hold back, like a gallon of water. I've seen 2 gallons per yard held back, and I think that's too much. I don't think you need to necessarily hold that much back, but I think if you hold back a gallon of water per yard, that gives you can't expect every truck to get there with exactly the slump that you're looking for. So that gives the contractor the ability to make those adjustments. It's important that the holdback water be clearly stated on the ticket so that you know how much water you have to make that adjustment. You don't want to exceed the approved water content on the approved mix design. But that's something that needs to get discussed during the pre-construction meeting. But in general, I have seen 1 gallon per yard holdback water work very well.
Okay, thank you so much.
You got it. You had one other question, I think, or was a comment about fogging above. Absolutely. That fogging, you're changing the ambient relative humidity. So that doesn't have to be only during placement and affecting plastic shrinkage cracking. You continue to fog.
We do lots of floors, interior floors, that are seamless. In fact, there are no joints. And so we fog for 7 days constantly. And I loved your picture of the fogging outside. I believe it was just a power washer fogging. And that, I hadn't done, but I think, in a long time, actually. I did it a long time ago, but that looked great, and that's pretty much the principle we use on interior floors is just to, mist and fog.
Yeah, you want to make sure it's a mist. You're not trying to flood the slab necessarily, and until it hits your final set, and then I guess the addition of water wouldn't be necessarily detrimental, but you're trying absolutely to keep that humidity as high as possible. The higher that humidity, a slab won't dry if it's in 100% relative humidity. That is going to continue to keep the moisture in the slab. So if you can achieve that with a mist, I think that's a great way to go.
All right. Well, thank you so much.
You got it.
And at this time, we have no further audio questions.
All right. I really appreciate it.
And thank you, ladies and gentlemen. This concludes today's conference. Thank you for participating. You may now disconnect.
Thank you.